Hi, and welcome to Mr. Garofolo's podcast. In today's episode, we are looking at Introduction to Compound Statements. Towards the end of class, we were working on example 4. I just want to pick up with some points of emphasis on this type of problem. So we had drawn two graphs on the same number line. This graph that we see here in green shows x is less than -4, and the graph in blue is x is greater than 0. And we're asked to consider which color highlighter shows where x is less than -4 or x is greater than 0. Well, remember, for or statements, only one of the two statements need to be true for the entire statement to be true. So therefore, we could pick a number, say, located in the green shading, say -5, and that would make this inequality true. Certainly would not make this one true, right? -5 is less than -4, but -5 is not greater than 0. But because it made one of them true, we would consider it a possible solution. Or if we picked a number from the blue shading, say +4, it would make this inequality true here, 4 is greater than 0, but it would make this one false. 4 is not less than -4. But remember, we only need one of the statements to be true for the entire statement to be true. So which color highlighter shows one or the other? Well, really both colors show that, right? Because anything that's in the green shading or blue shading at least satisfies one of the two statements. So in order for this to be true, what must be true about x? Well, over here, it's all numbers that are smaller than -4. On this side of our graph, these are numbers that are greater than 0. Well, numbers greater than 0 are, of course, positive numbers. So one way of answering this, and this is not the only way, would be to say that it must be a number that is smaller than -4 or any positive number. Any positive number would be this part of the graph, and these would be the numbers less than 4. So we go on to ask, would it be acceptable to write this as 0 less than x less than -4? Well, this is we'll call the compound inequality statement. And anytime we see statements that are written in this format, it's implied that an and would be connecting the two statements. So in other words, if we broke this down, this would be, one statement would be here, x is greater than 0, and the other statement would be right here, x is less than -4. So think about that for a moment. Is it possible for a number to be greater than 0 and at the same time be less than -4? Well, that's preposterous, right? There's no number that would satisfy both of those characteristics simultaneously. So in a statement connected by the word or, it is not permitted to write it as we see here as a compound inequality. So we would say, no, this statement implies that x is less than -4 and x is 0 at the same time, which of course could never be true. So what do we learn from this? Compound statements with the connector or may not be written in this format. So let's take a look at some graphs now. Example 5 asks us to draw some different graphs based on some compound statements. I'm going to select a couple and we'll try them. So let's look at B. X is less than or equal to 0. Okay. Or x is greater than 3. All right, so x is less than or equal to 0. That would have us including 0. So we would include 0 in our solution set. And the numbers that are less than 0 would be to the left. Or x is greater than 3. Well, that would not include 3. And the numbers that are greater than 3 would be to the right. So this graph would show any numbers that are less than or equal to 0, negative numbers, and 0, or numbers that are greater than 3. Notice how there's no overlapping of the shading. This is because the statement was connected using or. Let's try an and problem. So it says rewrite as a compound statement and draw the graph. Well, you'd be saying, what do you mean by a compound statement? Well, by a compound statement, I mean using the word and or the word or. Now, any inequality that's written as a compound inequality with a single variable here in the middle is implied to be an and statement. What we want to do is sort of break it down to see what are the two statements that are getting connected. So here's one of them. X is less than or equal to negative 1. So x is less than or equal to, positive 1. I'm just going to rewrite that over here. The other part of the compound statement also includes the x, but includes the other symbol and the other boundary number. Now, if we read this from left to right, from right to left, this says x is greater than or equal to negative 5. Greater than or equal to negative 5. So if we were to rewrite this compound inequality using an and, it would say x is greater than or equal to negative 5 and x is less than or equal to 1. So we're including 1 and we're including negative 5. The numbers that are greater than 5, greater than negative 5 would be shaded in this direction. Now I could continue shading past here, but I need to think about something. There's two conditions that have to be met right now in order for this to remain a true statement. One of them is that x must be greater than or equal to negative 5, and that's shown right here. However, the other condition is that x must be less than or equal to 1. Well, that would look like this. Let's just change the color up. I'll use black. All right, that would be this shading here. Now notice there's an overlapping section here. If you look closely, there's a section where the red and the black overlap. Right here to right here. That's our graph. So we're going to actually pull this shading back in, and we're going to pull this shading back in. I'll take out these little arrows, and that would be the graph describing this inequality. Okay? Your compound inequalities that are connected by the words and are going to have an overlapping or intersecting area. So this shows all the real numbers that are less than negative 5, greater than negative 5, less than 1, and it includes negative 5, and it includes positive 1. Let's try it the other way around. Here are some graphs in example 6, and we're asked to write them as compound statements. Let's look at A. So let's take this shading here. Notice it's a filled-in circle, so our boundary would include negative 2, and it's shaded to the left. So this would be all real numbers that are less than or equal to negative 2. This shading here shows that we don't include the 3, and we're shading to the right. So it's all real numbers that are bigger than 3, greater than 3. The question becomes, what do we join this with? Do we join it with the and, or we join it with or? Well, let's think about what this means. In order for this to be a true statement, using the word and, both of them have to be true. Well, is it possible that a number, say, from this shaded area satisfies both of those conditions? Let's try it out. 4 is greater than 3. That makes sense. Is 4 less than or equal to negative 2? Of course not. We can try a number from over here, negative 5. Negative 5 is less than or equal to negative 2. That's true. However, negative 5 is not greater than 3. Well, we're not going to be able to find any numbers that satisfy both. So this can't be a compound statement connected by and. It's an or statement. So we would write x is less than or equal to negative 2, or x is greater than 3. Let's look at B. So notice in B, we have two boundaries. There's no arrows here. That means that we have a beginning and an end to our set of solutions. So let's start with the left boundary. The left boundary is -3, and it's been included in the solution set. And the shading then goes to the right. So we're looking for numbers, values of x, that are greater than or equal to -3. Now, I've written that with the x on the right side. The reason I've done that is because we're going to write a compound inequality here using x one time. So this still means x is greater than or equal to -3. The boundary on the right side is a 5, and notice it's not included, and shading goes to the left. So those are the numbers that are less than 5. So we end up with this statement here. -3 is less than or equal to x, and x is less than 5. Now, if you wanted to write that out, it would look like this. X is greater than or equal to -3, and notice the use of the word and here, x is less than 5. Okay? What we've done is we've written both of these separate statements into one inequality, again, called a compound inequality. Let's take a look at some homework. Let's look at number 6. X is less than 1 and x is greater than 1. X is less than 1 or x is greater than 1. And then we're asked, does the change of the word from and, so and, to or, change the solution set? Use number line graphs to support your answers. So why don't you pause the video now, try writing out some number a number line and drawing the graph for each of these, and let's see if it makes a difference. Go ahead and pause. Okay, so I'm drawing some number lines out. Hopefully you did as well. Let's take a look at this first one. X is less than 1, so we would include 1, and greater than, excuse me, we wouldn't include 1. It would be an open circle on 1, and less, excuse me, and greater than -1. Open circle on -1. The numbers that would satisfy that inequality would be in between. Now we talk about the second one. X is less than 1 or x is greater than 1. So x is less than 1. That would look like this here, right? Or x is greater than 1. That would be an open circle on -1. And the numbers greater than would be this way. Now notice what happens here. Even though this was an or problem, there was no separation between the two boundaries. In fact, the boundaries crossed over one another and passed 1 and -1. Now let's think about if this is possible. Let's pick a number from here. Let's say -10. If we plug that in, we would have -10 is less than 1 or -10 is greater than -1. Well, the first statement is true, right? -10 is less than 1. The second statement is not true, but remember, we only need one of the two statements to be true for an or compound statement to be true. So we could pick a value that is past this boundary right here. Let's try a number that's past a boundary of +1, say 15. 15 is less than 1, or 15 is greater than -1. Well, 15 is certainly not less than 1. However, 15 is greater than -1. So once again, it satisfies one of the two statements. It's a true statement. Well, what does this mean? If we can go beyond these boundary numbers, and the shading goes through the open circles, past the open circles, infinitely in the negative and positive direction, well, we really have all real numbers here. So how does the solution set change? Well, we go from a finite set of solutions, right? A limited amount of solutions, if you will, only these numbers, to any number whatsoever could satisfy. Now, we didn't even try numbers in the overlapping. We should probably do that, right? Like maybe like 1/2. Just to solidify our understanding here. 1/2 is less than 1, or 1/2 is greater than -1. 1/2 is less than 1. That's true. 1/2 is greater than -1. Well, look at that. That's also true. Why do you think that happened? You guessed it. They were overlapping there. So both of them are true. So what happens in there, in the overlapping, both will be true. Once we get past those boundaries, only one of them will be true. But since it's an OR statement, we only need one. So the solution set certainly does change quite a bit. We go from a finite set of numbers to all real numbers. Well, hopefully this was helpful, and I'll see you in class.